Are these powders different medicines, or the same medicine in different concentrations? How can we distinguish visually identical samples? With the rise of opioid abuse and the developing legalization of marijuana in the United States, tools for quickly and accurately identifying a sample can be the key to saving a life or succeeding in a new market. At Hamamatsu, we understand that light holds a world of information. This motivates us to design sensors to decode the language this world of information is written in. One type of sensor we manufacture is a spectrometer, which takes broadband incident light and separates it into its spectrum. This spectrum can be in the ultraviolet, UV, visible, or the near-infrared, NIR, region of the electromagnetic spectrum. Information required to identify pharmaceutical samples can be found in the NIR. Working in the NIR can allow you to avoid issues that are typical of other spectral ranges. In the visible range, light leak can impact measurement accuracy, and in the UV range, UV radiation has the potential to destructively impact samples. So with the NIR range in focus, where within this range is most important to you? Since each compound reacts differently, we suggest doing research in the literature to find out what absorption or emission spectra exist in this range for your sample. From here, it becomes possible to match the spectrometer's range of sensitivity to that of the sample of interest. It's also important to know the granularity you'll need to resolve different peaks and the integration time required to detect a signal from the sample. The sample we're studying today is theophylline, which has known peaks from 1600 to 2100 nanometers, or for those who speak in wave numbers, 6200 to 4700 wave number respectively. Choosing a spectrometer to study this sample and other samples can come down to the spectra obtained. But why are these spectra so important to pharmaceutics? From research and development to process control and quality inspection, the information obtained through spectroscopic measurements contributes to unearthing key characteristics about medicines that can be used to track consistency in manufactured products or monitor for any errors. For applications focused on inline monitoring and process control, Hamamatsu has developed various compact spectrometer options which, when combined with a light source and sample handling, are capable of approaching performance capabilities similar to that of benchtop instruments. Here we have assembled tests comparing some of our NIR spectrometers for pharmaceutical studies. These spectrometers can be used to measure the spectrum reflected from a sample of theophylline, which has key peaks at 1664 nanometers. In these tests, we'll study the differences in spectra for theophylline samples at different concentrations. For these tests, we've utilized 3 of Hamamatsu's NIR spectrometer options: the FT-NIR engine, one of our MEMS-FPI modules, and our thin flat Mini-Spectrometer. Each of these tested with the same light source, sample holder, and optical fiber. These options are designed for compact and seamless integration of spectroscopic measurements in different regions of the NIR. When selecting a spectrometer, keep in mind that with different ranges of spectral sensitivity and different spectral bandwidths come varying windows of visibility to study the sample. Also pertinent is to take note of the resolution required. How far apart are the peaks of interest? Will the spectrometer you've selected have the resolution required to separate these peaks? The FT-NIR engine is used for our first test. This spectrometer utilizes a Michelson interferometer to scan across the NIR. We've designed this spectrometer to integrate the movable mirror and the fixed mirror into a single MEMS chip, ensuring reliability in measurements and stability in operation. Measurement signals are input to the FT-NIR engine through the collection lens and then focused onto the beam splitter. This light is then directed onto the movable mirror and the fixed mirror. The light reflected from the mirrors then rejoin at the beam splitter, and their interference signal is detected by the InGas photodiode. Simultaneously, a laser interferometer is used to track the position of the movable mirror. In this case, light from an internal VCSEL travels through the beam splitter to the movable mirror, is reflected back to the beam splitter, and the light is then detected by a silicon photodiode. Our free evaluation software provides the controls necessary for the FT-NIR engine to perform these actions in parallel, and the information gathered by both photodiodes is then collected. For original equipment manufacturers, or OEMs, designing their own instrumentation, we offer a full software development kit, or SDK. This free evaluation software can be used to gather interferograms as well as process them through techniques such as zero filling, which is used to enhance the separation of spectral features. These raw interferograms can also undergo fast Fourier transforms to produce measured spectra.
Moving on to a light source, we're using a source designed to optimize diffuse reflection measurements. Typically, diffuse reflection signals are low in intensity. This light source was designed to enhance the reflected signal through the internal structures seen in the diagram. Because the reflected signal from this light source is output through an SMA connector, we've prepared a fiber optic cable to direct the signal to the spectrometers. And since we're working in the NIR, we've selected a fiber optic material whose transmittance matches the required spectral ranges. The core diameter of this fiber is 600 micron, and its numerical aperture is 0.22 to match that of the spectrometers tested. We've also chosen to use a short fiber to reduce light loss. The length of the fiber used, however, should be tailored to suit your situation. Now let's begin by making a measurement with the FT-NIR engine. Using our free evaluation software, we'll set this measurement to a scan number of 128 and a gain of 1. There are 5 gain levels available in total. We'll then set our zero fill option to 2. We'll start by taking a measurement of our reference sample. After placing down the reference, make sure the measurement mode selected is Reference and click Measure. Once we've recorded the reference spectrum, we'll record the reflectance spectrum of each sample of theophylline. First, place down a theophylline sample with a concentration of 30% and click Sample. Change the vertical axis display to second derivative and the horizontal axis display to wavelength. Since our goal is to check the wavelength around 1660 nanometers, select the desired range on the graph and change the display range. Next, place a theophylline sample with 20% concentration and start the measurement. Finally, place a theophylline sample with 10% concentration and start this measurement. We're able to see the differences in the spectrum around 1660 nanometers for each concentration. We were also able to confirm the double peaks around 1660 and 1680 nanometers.
When we review the results, we see that significant peaks at 1660 and 1680 nanometers are combined. Applying zero filling to the interferogram results in better separation of the peaks. The resulting measurement accuracy is also very high, with an R-squared value of 0.9924 for a calibration curve at 1664 nanometers. The next spectrometer tested is the MEMS-FPI module. This module uses a different interferometer design, a Fabry-Perot interferometer. This interferometer consists of a tunable filter made up of upper and lower mirrors, whose distance apart defines which wavelengths of light in the NIR are transmitted through the filter and to the InGas pin photodiode. While the MEMS-FPI module is limited in terms of spectral coverage and resolution, it excels significantly in terms of cost and compact size advantages.
We'll now use the MEMS-FPI spectroscopic module to perform a measurement. When we operate this module on our software, we have the ability to turn on and turn off the integrated tungsten lamp. For this test, we'll leave this off, using an external light source instead. On our evaluation software, set the point averages to 1024 and the gain to high. After completing the gain setting, a message will be displayed. Press OK to close the message. Set the operation mode to measure and scan average to 1. We'll begin by collecting a dark measurement. This can be done by leaving our external light source off and clicking dark. Next, we'll collect a measurement of our reference sample by placing our reference sample down, turning on our external light source, and then clicking reference. And now we can measure our different theophylline samples by placing one of our various samples and clicking target. First, measure a theophylline sample at 30% concentration and switch the graph display to second derivative. Set the range to 10 and temporarily save this waveform under Save 3. Next, we'll measure a theophylline sample at 20% concentration and temporarily save this waveform under Save 2. And finally, we'll measure the theophylline sample at 10% concentration. From here, one can see the differences in concentration based on different peak intensities at around 1664 nanometers.
As seen in the data collected, due to its coarse resolution compared to the FT-NIR engine, the MEMS-FPI module does not record the peaks at 1680 and 1660 nanometers as distinct features. However, remarkable improvements can be made by a processing technique of taking the second derivative of the absorbance. Applying this process to the data enhances two peaks in the region from 1660 to 1680 nanometers. This process can be useful for various measurements which, at a glance, may not appear useful. In these cases, observable improvements can be achieved by applying a second derivative. The last spectrometer tested is our thin, flat Mini-Spectrometer. This device utilizes a grating optimized for transmitting NIR light and an in-gas image sensor to collect this light. In this instance, broadband input light is separated through the grating into its respective wavelengths before being focused onto the active area of the image sensor. When measuring different pharmaceutical compounds, again, it's important to match the spectral range required, whether that's absorption or emission, to that available on your spectrometer.
Finally, measurements will be made with a Mini-Spectrometer. Opening our evaluation software for this spectrometer, we'll select our key parameters. Here we'll input an exposure time of 2000 microseconds. Now this value can be increased to enhance signal collection and increase SNR, but please keep in mind that with increasing integration time comes an increase in dark current. Similar to the MEMS-FPI spectroscopic module, we'll begin by taking a dark measurement. We'll do so by leaving our light source off and clicking Start Measure Mode. We'll assign this data as our dark data under the Arithmetic Functions tab. Next, we'll place down our reference sample, turn on our light source, and click Start Measure Mode to begin our reference measurement. We'll assign this data as our reference under the same Arithmetic Functions tab. We can now move on to our sample measurements. Begin by placing down the 30% theophylline sample and clicking Start Measure Mode. Going back to the arithmetic functions, turn on the reference data display. From here, select Ratio Mode Display, and then click Auto Zoom. Here we were able to confirm double peaks at around 1660 and 1680 nanometers.
When we look at the data collected, we see two small peaks at around 1670 nanometers, showing that the differences in concentration were detected by the Mini-Spectrometer. This uncooled grating type spectrometer has sensitivity up to 1700 nanometers, covering points necessary to detect differences of theophylline concentration in a sample. The grating type spectrometer features fast response, so it should be the best option for inline measurements. Shown here are other samples measurable with these spectrometers. When measuring different pharmaceutical compounds, again, it's important to match the spectral range required, whether that's absorption or emission, to that available on your spectrometer. Here we see how the NIR range and resolution available on the FT-NIR engine, when tested in this setup, is capable of providing cost and size advantages compared to benchtop FT-NIR systems for analyzing various pharmaceutical samples. The devices presented today showcase the various spectroscopic technologies available for identifying and characterizing pharmaceutical materials. When we compare these technologies, we see how each of these designs contributes to different characteristics as seen in the table. These are just a few key specifications that need to be carefully considered when choosing a suitable spectrometer. Also keep in mind software integration. We make software integration simple with our full and detailed SDK, as well as our advanced technical support. An additional consideration to make is the method of data analysis to be used. With so many resources available, we encourage OEM design engineers and research scientists to utilize technical references and webinars to learn more about the requirements and expectations for spectrometer performance with respect to their application. Hamamatsu has many webinars available online, some on the devices shown today, and some on application discussions. You can check these out through the link in our description. Now, although this video focuses on the use of NIR spectrometers for the pharmaceutical industry, we understand that these spectrometers can and have been used in many other markets. For example, these technologies have been used in precision agriculture, moisture content monitoring, sugar content measurement, industrial chemical analysis, and thin film measurement. If any of these sound familiar to you, or if you're working on a completely different application, please feel free to reach out to us. We'd be happy to learn about your project and see how Hamamatsu can help. Thanks for watching.